Hello, I'm John Allers from the University of Idaho.
I'm Yadin from University of Arizona.
I'm Sarah Khalafinejad and I'm from University of Hamburg.
I'm Zhuoxiao Wang from Tsinghua University, Beijing.
Hi, I'm Rixin Li. I'm from University of Arizona.
Hi, I'm Jens Huimakers from Leiden University, Netherlands.
Hi, I'm Maximilian Gunter from the University of Cambridge, and I'm working on transits. Oh, and our acronym, as you see, is JPL, which stands for Jovian Planet Migration.
Okay, first we introduced some background and motivation. There's a big question. How can we form the short period planet? We all know some hot Jupiter and hot super Earth. We somehow they cannot form in situ. So we think there must be some migration, type 1 migration, type 2 migration. So here's the type 1 migration, and the first line they see the type 1 migration rate in the population census code, and the different mode describe the different gamma. There's a different gamma introduced by Ida and Lin and Paddy Cooper. The type 1 migration theory, the different mode is in isothermal disk or adiabatic disk. The theoretical part is Lindblad torque and the rotation torque. And in code, in the code there's also a scaling factor multiplied by here. So the different scaling factor describe the different different migration rate, and also there's type 2 migration introduced by these two kind of mode. There's mode 1, mode 2, also multiplied by the scaling factor here. Here, okay.
So, and the first question is, which of all these nice models should we in the end choose? Unfortunately, I ran out of time and couldn't put a picture for Alibet anymore. And if we look at this, we can compare with our known planets and do exactly what Doug Lin said we shouldn't do, and look at where do we produce planets compared to our known planets. So we ran through all these different modes, and for the first picture we fixed the type 1 to the Ida and Lin 2008 model, and the type 2 migration is plotted for the Ida and Lin 2004 in blue and the Alibert 2005 in red. And we see they basically agree in most parts, only we get a little bit less of those close-in super Earths around here. So all in all, we say, okay, we move from the 2004 to the Alibert 2005 because it's newer and Christoph did the same. But also because we find here in all modes for type 1 migration, of course, all these close-in super Earths that we don't observe. So we do a little bit of adjusting the theoretical model we use to the observations we do. In the second picture we see the same two type 2 models, but the isothermal model from Paddy Cooper et al. In 2010. And we see compared, I'm going to jump around a little bit, from the Ida and Lin 2008 to the Alibert 2010, there's not too much of a change. We get a lot of more stuff up here, but all these hot Jupiters are still lacking, and all this bunch that Kepler found us is still lacking. So we move on from the isothermal model to the adiabatic model, and we see this adiabatic model for the type 1 migration actually is able to reproduce most of these Kepler planets that we actually detect. So somewhat close in super Earths and mini Neptunes. But we're still lacking mainly all those hot Jupiters. And that leads to our second research question. We're going to fix now also our models to the type 1 adiabatic model and the type 2 Alibert 2005, because we do not observe all those, so we restrict this choice to our observations. And the second research question is then given by this. How can we produce hot Jupiters, and in the end, how can we not kill them after producing them?
Yeah, so what we're basically translating this into code is trying to balance the two migration rates that we have in order to, at the same time, produce the Kepler targets, the icy giants, and also the hot Jupiters. Basically, that means having enough migration to migrate the Jovian planets towards the star without actually eating them up, but stopping them, so that we are left with a significant hot Jupiter population. Now, to do this, we wanted to vary our type 1 and 2 migration rates, and we were at first using Christoph's default values, but we were not really sure how, because they are very, very low, they're like 10 to the minus 3, both of them. We were not really sure how realistic that was, so we wanted to vary them over a pretty large range. So what you see here is the plot of the parameter space of type 2 migration versus type 1 migration, and each of these dots shows one of the runs that we did. We ended up doing about 500 runs last night, and that allowed us to produce also a few videos. Now, these videos, they might flicker a little bit. That's because for each run we were using a different random seed, which is very good statistics-wise, but not so good animation-wise. And what we're doing is we are keeping, first of all, migration type 2, we are shutting it off, and we vary the migration 1 rate to see what migration 1 on its own manages to produce for us. And as you can see, as you increase type 1 rate, you start moving planets from here, where we don't have any detection, towards the icy giants and somewhat towards the hot Jupiter population. At the same time, these super-Earths, they move across what we observe towards areas where we think that they are prone to being eaten by the star. Now, what we failed to basically do is maintain this population. So migration type 1 migrates all these planets towards the star, but does not stop them where we want them to stop. So, what is this? Now we keep the type 1 migration rate fixed at the default value, and instead we vary migration rate 2, excuse me. And again, we get something similar, and this time we are less able to reproduce this hot Jupiter population, while actually doing a fairly good job on the icy giants and super-Earth population. So what we end up seeing is that we need to balance kind of these two. We need really type 1 migration in order to maintain these two populations, and we do a fairly good job at that, but at the same time we need type 2 in order to reproduce hot Jupiters. And finding that balance is a very, very delicate thing, which we actually didn't really manage to do because the parameter space is very big. But we are confident that we could, if we had a couple of nights more of simulation time, find some sort of a balance that would actually produce hot Jupiters there. Now, we also did some KS tests to find the right balance, but since we have learned today that KS tests are a very bad idea, we actually decided to drop that. Now, I would like to note that the KS values we got in the previous talks, they were like ranging between like minus 100 and minus 200. We actually got a couple of minus 10, minus 9, so in that sense I think we were doing a pretty good job for what that is worth. So on to our conclusions.
So yeah, to finally summarize all that, we've seen type 1 migration can give us a lot, but not the hot Jupiters, and type 2 migration then can explain our hot Jupiters. However, we saw if we let the type 2 migration get too mighty, if the migration rates get too high, they alone are too strong. All the hot Jupiters would get eaten in the end, as we saw in the last pictures. So we need some kind of trends that preserve the close-in planets. And those trends could, for example, be tides that would preserve these close-in hot Jupiters. And that would be a point of future research, and all that's left to say is Christoph needs to implement tides in that code. Thank you very much. Yeah, I think that leads back to, to summarize the question, it was how well would we do if we would leave out the population of hot Jupiters and not look at them that much, but only look at the icy Jupiters and the hot super Earths, etc., that we find, assuming that the hot Jupiters would be, come in that close by, for example, dynamical scattering. And the question to that, I think, was in the middle of the presentation around, we saw in one of the movies, when we leave out the type 2 migration and we drive up the type 1 migration, we can actually pretty nicely, by eye in these videos, reproduce these populations of close-in super Earths and mini Neptunes and far-out Jupiters. So that would be another thing to look at actually implementing, or in our runs, implementing the possibility of looking at the dynamical scattering as well and alternating that as a contrast to the type 2 migration.